All right, sorry for the delay. IT is working on a projector. Okay. I wanted to talk a little bit about the midterm next week. Okay, before we start lecture. So midterm, it's going to be on October 11, okay, which is a Wednesday. Okay. And so we're going to start at 7:15 because I understand you guys have some of you have a lecture ends at 6:30. So we're going to start at 7:15. Okay. Now this is for this section, right? So this is section 101, I believe you did. Are you guys in the right section here? Yeah. Okay. Because we have two sections, so you will go to FIPK 204. Okay. Yeah. So the other section will go to a different room. So make sure to come to the right section, though, huh? Yeah. And we're going to start at 7:15, and it'll last for 1.5 hours, so it will end at 8:45 p.m. Okay? Yeah. So that should be enough. That's not too late. You can still catch a bus if you want. Okay. Yeah. Now, in terms of the material we're covering, we're going to cover until basically today is lecture 8, and Thursday will be lecture 9. So basically until the lecture 9. Okay. So according to my lecture number. Okay. Including? Yeah, including. Yeah, including. So basically it includes this multivariable function and its multivariable calculus. Okay. So including L1 to L9, or L9 is the October 5th lecture, right? In terms of assignment, it's assignment 1, 2, 3. Okay. And you do have 2 additional exercises you can find that are on the Connect. Okay. So one additional exercise is on the lines and the planes. The other one is on the partial derivatives. Okay. So that's basically the midterm. The midterm is going to be closed book, so close everything. Okay. No, you don't need a formula sheet. There isn't many formulas. If you need a formula, for example, like lines or planes, you just write down a few times, it'll be yours, right? Yeah, that's it.
So does that include in the textbook up to the end of chapter 14?
I believe so. Yeah. I don't have my textbook here, so, but yeah. If chapter 14 is the partial derivative, then this, yeah. Any questions? Okay. Yeah. So midterm, based on my experience, okay, students typically did in the past did really well. Really well doesn't mean that really well. So normally they did well enough, okay, compared to final, because my midterm usually a little bit compared to other courses a bit of a early midterms, okay. So I shouldn't be too nervous about the midterm. Okay, as long as you do all the assignments independently, prepare all the for the lecture notes, lecture materials, I think you should be okay. Okay, yeah. So they're probably going to be around 3 big questions. Okay, so there will be definitely a question on lines, planes. There will be a question on the scalar line integrals. Okay, yeah. There'll probably be a question on the partial derivative. So those big topics, right? Yeah. And there's some small knowledge points that you should also be comfortable with. Okay. Yeah. Okay. So let's finish this scalar line integral today. Okay. And then we'll get on to this multivariable function and its calculus. Okay. Any questions? Good. Okay. We learned about scalar line integral in the previous lecture. Basically, we're looking for if I have a curve C, okay, and it goes from t equal to t1 to t equal to t2, and curve C can be represented using the parametric equation or vector function R of t. Then scalar line integral basically is talking about is to integrate a function f of x, y, z, okay, over the curve C. Okay, so this is basically a scalar line integral. And this function f of x, y, z is, we said this is a function defined over the curve C. And all it means essentially define over curve C. If you pick a point on the curve C which has coordinates x of t, y of t, and z of t, then you plug that point into the function, it has something returned to you. Okay, so that's essentially what the define means. IT is doing this. This one's not. Oh, I'm back. Okay, so can you guys see here? Yeah, barely. Yeah. Okay, so let's continue here. So let's take a look at the example. Okay, this example I didn't get to finish this example. So let's finish the example here. It's fairly straightforward. Basically, in this case here, we're trying to integrate over a curve C, which consists of two segments, curve C1 and curve C2. And we did actually the parameterization for the curve C1 and C2 in previous lecture. So in this case, let's just write it down again. So for C1, it's a straight line here. So we can use TT representing this parametric, representing this straight line here using this parametric equation. The range of the t, because it goes from origin to 1, 1, 0, so the range of t goes from 0 to 1. Okay, so that's your t's range. C2, okay, let's call this is R2 of t. It's also straight line, goes from 1, 1, 0 to 1, 1, 1. So the x and y not changing, so it's still 1 and 1. And the z component goes from 0 to 1. So we use a t. And the t goes from 1 to 0, 0 to 1, okay, similarly. So that's your parameterization for curves R1 and R2, or C1 and C2. Okay. So finally, time to plug this into the into this line integral formula now. Okay. Now because C. Okay. Did you do that?
Yes, he just pushed a new program that should fix this. So
okay.
Give it another 30 and then I'll get you up on both screens.
Sure. Sorry, I'll let you. Yeah.
We're pretty much at the mercy of the program restarting right now.
Yeah. Next time I should bring a marker with me, just in case. So you're the one you find here. They are running out of ink.
Okay, let's see. There we go. All right, and we want this up, and this up.
Good.
And
Yeah.
beautiful. Here we go. Let's make sure this one's up.
Yeah, let's turn on it. Yeah. All right. Thank you very much. Okay. Good. Back to life here. Okay. Okay, so this is the line integral we're looking for. Now, because the C1 is equal to the C equal to C1 and C2. Okay. So all we need to do, basically, we need to do this so-called piecewise integral at here. Okay. So let's deal with each one of these separately at here. C1, okay, the first piecewise integral. Well, I don't know why the microphone's not working now. Is it working? Yeah. Oh, okay. Okay, so a little closer. If you recall, the formula for line integral involve two parts. First of all, you need to replace the x, y, z with x of t, y of t, z of t. And second of all, you have to find the ds component, right? Okay. So let me write down this a little bit here. So x of t, y of t, and z of t. That's what we're going to replace. And ds, if you recall that, is equal to this dot product, derivative of r1 and dot itself, take square root, and then dt, right? Okay. So now let's take a look at everything here. What's the function f here? The function f is given over here. So for C1, we need to replace the x with x of t, which is t. We need to replace the y with y of t, which is t at here. And we replace the z with 0. So, and t's range is from 0 to 1. So you can put the limits at here for 0 to 1. And x is replaced with t, y with the t square, y with the t, so 3t squared plus 0. And then derivative. So dr1 over dt, dr1 over dt. So you look at the derivative here. So this t derivative basically was 1 at here. If you want to write down the 0 for the z component, that's fine. And same thing, 1 0 dt. Right, so that's how you put things together for this C1 segment. Multiply this out, and it's a very simple integral set here. Okay, so we get 1/2 t squared minus 3 over 3 over 3, which is t cubed. Okay, and the t goes from 0 to 1, and the square root at here is 1 times 1 plus 1 times 1 is 2, square root of 2. Okay, so that's the integral for this one, right?
Shouldn't the x have been squared?
Shouldn't be x squared? Oh, sorry, actually I wrote it down here. There shouldn't be a square here. Yeah, sorry. Okay. So x minus 3y squared plus z. Okay, so plug it in here. So 1/2 minus 1 is negative 1/2. So negative root 2 over 2. So that's the results for the first segments, right? The first segment here. And you can try the second segment with a very similar approach, basically the same approach. Your t also goes from 0 to 1. But in this case, your x of t is 1, y of t is 1, and z of t is z of t is t. So replace that with x, y, z. So you get 1 minus 3 plus t. And then dr1 over dr1 over dr2 over dt, constant t, so 0, 0, 1. Okay, so that's basically the results for this portion. So then you put things together. This one just give you 1, and this one give you negative 2 plus t dt. So that give me negative 2t plus 1/2 t squared. The t goes from 0 to 1. So plugging 1 over here, so negative 2 plus 1/2, so that's negative 3 over 2. Okay. Finally, your total line integral is negative root 2 over 2 minus 3 over 2. Okay. So that's the typical kind of question for piecewise line integral, right? Okay. Yeah. So the key point that here is, okay, if the question didn't give you the parametric equation for the curve C, then you had to come up with one, right? So I mentioned in the previous lecture, you don't need to worry about too complicated, just very common ones, like a circle, like a typical curve, and like the straight lines, like this case here. Okay, what are the suitable parametric equation? And what's the range for that? Okay, so that you need a range. Okay, so finally you put things together, and then you get the line integral. Now, in my previous lecture, I mentioned about the physical meaning of scalar line integral, and I compare that basically with a simple integral of a single function, a scalar function. Okay, and we know that this basically represents the area underneath the curve, right? Yeah. And we also mentioned that if we use a similar analogy, then let's see. But then similar analogy basically means I'm considering it's a curve C in 2D space. Okay, this is in 2D. So like the example we did here, it's for curve C in 3D space, right? Yeah. I mean, you can get rid of one variable, and then it basically it's a line integral in 2D space. Okay. So if it's a line integral in 2D space, so you have a curve C, which is this is C now. This is your 2D curve instead of a 3D curve, and then you have your f of x, y defined. Okay, so that's basically a surface in the 3D space. Then when you going or integrating along the curve C, it's like you're constrained along this curve C. So there will be basically a similar curve tracked out on the surface, and that's f of basically this one here is your f of x of t and y of t value here. Okay, yes, constrained over there. Okay. So if you do this integral, you'll get a similar analogy. You get the area underneath that curtain, basically. Okay, yeah. So that's better understanding basically what the line integral is. And of course, we also related if this function and here actually give a meaning called density, then when you finish this line integral, what you get is actually the so-called mass, right, for the wire. Okay, so this all depends on how you can interpret it. So I'll give you a very simple example. You can actually verify this this idea here. Okay, let's say I have a curve C. Okay, here's a curve C, in the 2D plane, it's a straight line. So it connects from one point to another point, curve C. Okay. At the same time, I have a function f of xy equal to 4. So that basically is z equal to 4, okay, which I will touch upon this actually after example. This is the plane, right? You know, when you see z equal to 4, it's a plane parallel to the xy plane, okay? And then if we're going to integrate, this function f of xy over the curve C, right? That's the line integral, scalar line integral we're going to try to look for it here, right? Okay, yeah. Okay, so if this is scalar line integral you're looking for, before you can calculate, right? Before you calculate this, use the idea I just mentioned. What does this represent again? It represents basically the area, right? Okay. Can you try to just use without calculation, right? Can you get the area or get the scalar line integral at here? What would that be? 8 root 2. Oh, almost there. 4 root 2. Yeah. Well, so basically, if you go from here to here, basically, what do we track out? We will trace out. We'll trace out a straight line on that surface, right? As you are going along that curve C, okay? And then you connect everything. What you see here is basically a rectangle, isn't it, right? Okay. And the height of the rectangle is 4. And what's the base length of the rectangle? It's this hypotenuse, right? Okay. And that's the basically 2 at here. So this side here is what? 2 root 2. Okay. Oh, sorry. Actually, it is 8 root 2, right? What's going on here? Yeah, that's right. Yeah. Okay. So then the total area is 8 root 2. Okay, if I do the calculation, actually, my notes here says z equal to 2. But anyway, so now if I do the calculation according to the formulas that we learned, the formal procedures here, okay, then what do we need to do? This is a curve C. So first of all, we need to parameterize the curve C. So the curve C is x plus y equal to 2, right? Equal to 2. So I can parameterize this curve C by doing this. By, for example, I'll let x equal to t, then y equal to what? 2 minus t, right? So basically, you let x equal to t, and the y will equal to 2 minus t. Okay, that's how you parameterize that straight line. And what's the range for the t in this case? It goes from one end to the other end. So the t range starts from 0. So as you go from, is that right? So initially x equal to 2, right? So x equal to 2. So I guess I should let t equal to 2 initially. Okay? Yeah. And then 2 goes to where? To 0. Okay? Yeah. So when to 0, you got a 0 here, 2 here, so you end up at that location. That make sense? Okay? Yeah. So that would be the range for the t at here. Good? Okay. Okay. So now you put things into this equation. So what do we get? We get replace x with t, replace y with 2 minus t, but then your z equal to 4, right? So really nothing changed. Still 4 at here. Okay. The ds equal to dr over dt dot dr over dt. Okay, and dt, and t go from 2 to 0. Okay. So your R at here, okay. This is R of t, so that's 1, -1, dot 1, -1 dt. Okay. I'm going to get a negative sign here. So 4 times 1 times 1, so that's √2, right? dt. So overall, I would get, how come I get a negative here? So I get a -8 √2. What's going on here? Do you see any mistakes over here?
If you're going from 2 to 0, you get a negative, right?
Yeah. But if I go from here to here, that got to be from 2 to 0, right? If I go from 0 to t, oh, 0 to 2.
And then your x is 2 minus t, and your y is t.
Oh yeah, that's right. So we changed that to t at here, 2 minus t at here. Is that right?
Yeah, and then you flip from 0 to 2.
That's right. That's right. So that'll give us a positive number now. Interesting. So how come if when I change this, I got a completely different numbers? Okay, you guys think about this, okay? Yeah, I have a that's interesting. Yeah, I'll think about it too. Yeah, I don't think what I did was wrong. The other one, right? I don't think what I did was wrong. The direction matters basically. The line integral direction matters. So one direction give me a positive, the other direction give me a negative at here. Okay, but how does that relate to the area? Interesting. Okay, so let me think about this. But in terms of the procedure, okay, any questions? All good? Okay. Yeah. Okay. So let's continue from here, right? Yeah. Now we're going into a new topic here. So let's look at functions of multivariables, okay? And then we'll look at its calculus. Okay. Multivariable function, as the name suggests, basically you have a function. Okay, instead of just a single variable at here, we can define or insert as many as possible. Okay, into this function. So that's a function of a multivariable function here. Okay. So if I see it here, so basically W is a function of so-called n-tuple, x1, x2, and up to xn. So there are a number of variables here. Okay. So you have a n number of independent variable at here, and then return back to one independent variable w, right? Okay, that's function multivariable. So far, I think up to now in your calculus course, you have all learned is about basically a function of a single variables here. Function multivariables are very useful. Okay, especially we're going to focus on is a function of basically we're going to focus on function of two variables. Okay, and maximum we're going to look at is function of three variables. Okay, so that's what we're going to focus on in here. Now, just like a function of a single variable, before we talk about its calculus or its derivatives, let's basically try to establish some sort of idea. What does this function look like, or even whether we can even graph it, right, to establish the sketch of this function. So first thing that you got to establish here, if this is a function of two variables, so in terms of, I can use a z here, doesn't really matter, okay? In terms of function two variables, you can always sketch that in 3D. Okay, so this is just sketchable, okay? So you can sketch this. But in terms of function three variable now, then you can't, okay? So basically, you can generate a graph for function of three variables, okay? But we have a different way to try to visualize function three variables. I'll cover that shortly, okay? So first of all, let's take a look at basically some graphical example. Okay, some graphical examples for function of two variables. Okay, so let's just take a look at some graphical. So what does it look like? Typical functions. Function of two variables actually not really new now. If you recall that in the previous lecture, we derived plane equations, and this is a plane equation here, right? Okay, so this essentially actually is a function of two variables, because I can always rewrite z such that it's equal to d minus ax minus by and divided by c. Right. So I can always write it into this, and this is exactly in the format of f of x, y. Right? And that's a plane. We already learned that when you have a z equal to this kind of format here, that's a plane. Okay? Yeah. So, for example, if I have a z equal to negative y, okay? So that's a simple case. Okay, from here, this is a plane here. Okay, this is a plane. So when you draw a plane, all you see is, you can always draw a plane in 3D space. It dissects the whole space into two halves, and that's a plane. Now in this case, often in time, so when you look at this one here, when you see, okay, z equal to negative y, that appear to be just a function involving two variables. If you think in terms of, let's say, just the z and the y coordinates, and that's probably, that's actually a straight line like this. That's probably a straight line, right? If you only look at it from the planar case, okay? Yeah. But in the 3D, you can always extend from this line here up and down, okay, and then they'll give you the plane. Okay, so that's basically what this one looks like here. Okay. So sometimes you only have a function of maybe like this, y equal to x, right? That's a function of two variable, right? That's a straight line. But in 3D, it's actually a plane. Okay, yeah, or even just z equal to 4, right? Like the example. So that's z equal to 4. That's a straight line, but then you extend that, and I give you a plane. Okay, so that's something that you need to establish it here. Okay. So that's one example here. Okay, yeah. So that's one example. Some other examples, essentially like this one here. So what I'm showing you at here, okay, are planes or surfaces that I expect you to be able to construct in your mind whenever you see such kind of expression during an exam or during assignments. Okay, yeah. So let's say if I have this expression here. So z equal to 1 minus x squared minus y squared. Now this is not a plane anymore, right? Because this is not in the plane equation format. Okay. So what does it look like then, right? One way you can imagine this is essentially is, if you look at this, z equal to 1 minus x squared minus y squared. X squared, y squared, a quantity is always what? Greater than 0, right? Okay. And then you have 1 minus 2 positive number. So basically, the maximum number for the z must be, what's the maximum number for the z at here? 1, right? Good. So if you plot this out, and you'll see that it's essentially an inverted, like a bow kind of curve like that. Okay? Yeah. So it's an inverted so-called parabola. Okay? Paraboloid. Okay? So this essentially is a paraboloid type of shape. And similarly, if I give you, let's say, z equal to x squared plus y squared, and that's the one that we use quite a bit in the near future to illustrate a different type of examples. That's a surface, just like this one here. This is so-called, we call this surface, okay, including the planes. So this one, if you plot it out, okay, in 3D space, it'll be a paraboloid, okay, which is pointing upwards now. And in this case, your z has a minimum value, which is 0 at here. Okay. And in this case, the z has a maximum value 1 over here. So that's how you can visualize this z, the type of paraboloids. Okay. Yeah. Another one, very useful one, is this one. So z equal to x squared minus y squared. Now this one here, I'll show you what it looks like. Okay. So this is the shape of the z equal to x squared minus y squared. Okay. What does this shape remind you? Saddle, exactly, right? So why do they call it saddle then? Because if you look at this surface at here, you look at this point. This is point, we call it saddle point. At this location, if you go this way, you're actually what? Going up, right? But if you go this way, it's going down. So that's called a saddle point. So this point is either the minimum nor it's a maximum. Okay, just like in function single variable, there's a similar point. If you recall that, we call that what kind of point? In function of a single variable, inflection point, exactly, right? Yeah. So this is a saddle here. This is called a saddle surface. Okay. Yeah. Later in the future lectures, we actually would try to look for is how do I look for the minimum point, maximum point, or how even we can find the saddle point. Okay, so that's something that we're going to look for in the future. Another example which is also interesting, and this one here, I'll write it down first, and then we'll look at the difference. Okay. So this is another example right here. Okay, this is another example of a function of involving x, y, z. Okay. Now, when you look at this example compared to the previous three examples, okay, compared to the previous examples here, can you see any difference? What's the difference now for this one here? Or just simply compare to z equal to, you know, x squared plus y squared, for example, right? Pick a point. Sorry. What's the difference?
Function of x, y, and z.
Yeah. So here you have function f of y, f of x, y, right? But what about this guy here? Can you write this out into z equal to f of x, y, z? Probably you could, but it's hard, right? Yeah. So basically, for this example here, that x, y, z is all, tangled together. Okay. So this one we call it implicit. Okay. Implicit function. Okay. Implicit meaning you don't have like this one explicit expression for the z. Okay. So that's what it's called implicit. Right? Yeah. But it's still a surface because it involves three variables x, y, z. So it's still a surface here. And as a matter of fact, this is a very beautiful surface. And if you plot it out, and you got a heart. Okay? Yeah. So this is a surface found out by a guy called Tobin in 1994. Not too far away, actually, right? Yeah. So honestly, I don't know how he can construct a surface out of all of these things here. It's just completely out of my boundaries here. So, and actually, okay, so I want you to try. I'm going to upload you some Maple files here. There is an alternative to this hard surface, which is by another guy constructed in 2004. So it's a similar order, okay, same order here, but a different expression. Now this is the heart from his construction. If you compare, they're actually different type of shape of hearts. Okay, yeah. Try it out, and then you can give a different kind of shading, different kind of color. Okay, one of the previous students actually printed out, give it to his girlfriend on the Valentine's Day next year. So it worked really well, I heard. So, and this equation, okay, and this equation also has a pretty good name. It's called the sextic equation. Okay? Yeah. That's the real name, huh? So, because the order here is 6, okay, the order here is 6. Equation-wise, if you recall that from what's the lowest order? Constant, right? And then first order linear, and then quadratic, cubic, quadic, quintic, and then septic, and the next one is septic. So anyway, so you can find actually many other different examples, okay, for surface. They are like this one. I have a couple of it here. So if you give a different shape, you get basically a different type of surface. Okay? Yeah. So you can really construct some very beautiful surfaces. Okay. I have some more examples. Some examples don't have time to show it here, but if you're interested, I'll show you. Okay. Yeah. So what I need you to basically at this stage, for very simple surfaces like a plane or like the x squared plus z equal to x squared y squared. Later we have a cones, okay. This is or cylinders. So we need you basically to be able to tell what they look like by writing down when you see such kind of expression, right? Yeah. So that's a surface. What else can we do basically to visualize a surface then, right? So another portion we can show is a so-called contour plot. Okay, it's called a contour plot. This is also a very useful tool, especially if you're going into civil engineering. I mean. Or if you're going to read a map or something, right? So what is a contour plot? Contour plot, basically, I'll just quickly go over it, okay? So contour plot, essentially, you slice this surface or the plane with a constant plane, layers of the plane. So for example, in this case here, if I have, let's say, z equal to negative y, right? So that's a plane, right? That's a plane. And now you let z equal to, you slice that with a different plane. Basically means you let z equal to 1, and let z equal to 2, or 3, and you keep going. Okay? So when you say let z equal to 1, 2, 3, they're actually planes. Okay? So they're actually planes, right? So when you slice that, basically you substitute z over here and 2 over here and 3 over here. Okay? So the results of the slice give you what? Give you a straight line. So y equal to -1, y equal to -2, and y equal to -3. Now this is essentially the so-called the contour plot. So when you project all the lines, okay, into one plane, then you get this so-called contour plot. So I'll show you one more example right here. So like this, okay, so z equal to 1 minus x squared plus y squared. So let's write down here z equal to 1 minus x squared plus y squared, like this, okay? Yeah. So I'm gonna slice this surface, okay, slice this surface using a cluster of planes, z equal to a certain number of sequence of numbers. So for example, if I let z equal to 1, okay, then we get x squared plus y squared equal to 0, right? Okay. If I let z equal to, let's say, -3, so we get x squared plus y squared equal to 4, right? Yeah. So when you slice this surface using a plane like this, what do we end up with? We end up with basically what? A cluster of circles, right? The circles here. So that's the circle. So then you can always project all the circle onto the xy plane. So you end up with a cluster of circles. That's the contour plot. Okay. Yeah. So essentially, contour plot for z equal to fxy is you slice that with a different z value. Okay. Yeah. And same thing, similarly like this function in here. Okay, there are two bumps. One goes up, one goes down. And you slice that, then you get two cluster of circles. Okay. And then for this one, the saddle, okay, and you can get the contour plot like this. Or if you simply slicing a regular mountain, then you get contour plot like this, right? Okay, yeah. So that's contour plot. And when you slice a contour plot, one way to give more information is not just draw the curve or the contour plot. Okay, we call this each one of the curve. We call it a level curves. Okay, so basically, there's a term here now. It's called level curves. Okay. So what is a level curve? It's like the name says. Along each curve, it's the same level, right? That's level curves. Okay. So basically, it's a one contour. Okay. So if I look at this one here, right? Let's say if I look at this contour plot. Okay. So this is like a plane you're climbing here. So you look at the contour plot, and you look at this one here, this side here. Say, okay, so this side has a very small space between two adjacent contours, and on this side here, there more space out, right? Okay. So what does this information tell you? Basically, the information tells you is over this side, the mountain, it has much what do we call that? Steeper, right? It's a steeper ramp. And over here, it's less steep. Okay? Yeah. So that's what you can tell you, right? Yeah. However, okay, I don't think that information is accurate enough, right? You know, as a mathematician or engineers, you don't want to just say, oh, that side is steeper than the other side. How steep? You know, what's the slope on this side here, right? So that the contour plot, unfortunately, cannot tell us that precise information. Okay? Yeah. So what we really want is we want to know a certain kind of slope concept, right? You know, basically, here's a surface, okay, and any type of surface. Now I'm going to try to climb up on this side here, right? So the question here is how steep it is, or what's the slope on this side here, okay? So that's what we want to actually more often we want to be interested in. For that surface, what's the slope on this side here, okay? Yeah. And more actually into the question later is, imagine this surface here, right? If you go up this way, there's a surface, right? When you climb mountain, but not only you don't actually go up, you probably will actually go like this way, isn't it, right? Yeah. Now, when you go at different directions, guess what? There are different what? Slopes. Okay? Yeah. And that's actually what we're going to cover after midterm. That will be so-called directional derivative. Okay? Yeah, as we're going along the different directions. Okay? So, but it's all a type of slope concept. Okay? So that's what we want to figure out more precisely, how to get the slope concept. And this will be answered using the next knowledge point, which is the so-called the partial derivative. Okay? Yeah. Okay. So that's what we're going to look at. But before we look at the partial derivative, see so far all I have illustrated is a function of two variables, right? Yeah. So I did mention that we also will look at function of three variables. Okay. Yeah. Now, how do I visualize a function of three variables then, right? For starters, you can't graph it. Okay. So you can't visualize as a surface in a 3D space. Okay. But then we can use a very similar idea. So for function of two variables, what the second one to use what is contour plots, right? We use a contour plot to visualize this surface. So for function of three variables, let's use a similar idea. So what we do is we let w equal to a let w equal to a constant c. Okay, yeah. So for example, we let w equal to 1. We let w equal to 2, like this, right? This is what it means said here. Okay. So originally you have a function of three variables, okay? 1, 2, 3, and now we are making the w to be a constant, different constants. By doing this, what do we end up with, right? For each one of this, and now they are becoming what? Becoming a function of 1, 2, 3 now. Only three variables involved instead of 1, 2, 3, 4 involved. Does that make sense? So each one of these is basically, it's a surface now, right? It's a surface now. And then we have a better yet, we have a name for it. It's called a level surface. Okay, it's a level surface. Why is it level? Because on each surface, the w is the constant. It's 1. Okay, that's what it's called a level surface. That makes sense? Yeah. Now, how's that going to help us? I'll give you an example. Let's say I have x squared plus y squared plus z squared, w equal to this, for example. Okay. So I have a w equal to x squared plus y z squared, and then we don't know what it is, right? Let's try the technique at here. Try the level surface idea. So we're going to let w equal to what? Okay. Now what does that look like now? X squared plus y squared plus z squared equal to 1. It's a sphere, right? And with a radius of 1. So if we let the w equal to a different number, that's called a c squared. Okay. So now it's the same. It's still a sphere, right? And it's a sphere with a radius of c now. But all the sphere, they all have the same origin, isn't it? Right? Yeah. So now you can imagine for this function of three variables, it's basically, you can imagine it's like layers and layers of orange, basically, right? You peel one layer and there's another layer. So that's how you can visualize, right? Yeah. It's not a concrete object, right? But it's something that you can at least to give you some idea what it is. Okay. Yeah. So that's for function three variables. So we use the so-called level surface to help us not really visualize, to try to better understand what this one really can be described as. Okay. Yeah. So far you look at the graphic examples of the typical functions and how you can draw level curves or contour plot, or how you can draw level surface. Okay. Yeah. So there's a very basic stuff associated with the multivariable functions. Okay. Yeah. Now let's look at the calculus for multivariable functions. Okay. Now this is not really going to be new, so I'm going to basically give you a heads up here. It's new, but it's not new. Okay. Now let's start with the very simple one: function of single variables. When you do derivative function single variables, and here's the definition. Okay. So that's function of single variables derivative. Okay. Of course, mathematically it's called derivative, but often in time we also describe that using simple words, like in this case here. Right? If you look at this ratio at here, right? You look at the ratio here. Essentially, we can call this is the rate of a change, okay, with respect to change of x. So, how much this f function change when you have a small change in the x variable and here, okay? Yeah, that's single variable. Now, for function of a 2-variable or 3-variable multivariables, so let's use maybe function 3 variables as an example illustration here, okay? So let's say I have a function of 3 variables in here. Okay. Now, what we're gonna try to derive here is what is the rate of a change of this f, okay, with respect to x direction change. Okay, so all with respect to x. Okay, so partial derivative from now on, you actually will notice there's a introduction of a so-called direction now. Okay, yeah. Direction basically means I'm here. I can actually have a small change in that direction, a small change in that direction, right? Yeah. So that's basically the idea we want to find it out here. Use the similar expression, right? Use the similar expression in here. So we're talking about x change here, so divided by delta x. Function f, there's a change in the x direction. Okay, so we only have a change in x direction. So the y and z value, no change. Okay. Okay. There we go. So that's the similar definition, right, as we used for single variable function. Okay. Now this one here is actually the definition of partial derivative. So instead of the straight d now we use this so-called curved d. So you can write it like this, okay? Yeah, or write that. Yeah. So you can typically write it this way. Okay? So this is called a curved d, okay. And that's I normally call it straight d. And this sign in here, you can also call it partial. Okay. Yeah. So we can, for example, when you have this one here, you can pronounce it as partial f over partial x, or you can say it in the very formal expression, partial derivative f with respect to x. Okay, so that's how you can express that. Okay. There. So that's partial derivative of f with respect to x. So the only change is there's the adjective words partial now, right? Okay. Yeah. Now remember in the first lecture I mentioned about your journey of calculus. So from straight d to partial d, so you're at the partial now. Okay. Yeah. And the next one is, if you recall that as well, right? It's this guy here, Stel. Okay. Okay. Now you can similarly find what the partial f over partial y is, and what the partial y is over partial z is. Okay. Very similar. Good. Yeah. For partial derivative, just notation-wise, we have. In terms of so partial f, hopefully partial x, this is basically notation wise. Okay? We sometimes also write like this. So f subscript x. Okay? Yeah. So when you see that, it's the same thing. Okay? Yeah. And this is the first order, okay, derivative. Okay. This is the first order derivative. Just like df over dx is first order. And you do have a high order. Okay. For high order, for example, if we have partial f or partial x, and we can take another partial derivative, okay, with respect to the x, once you get the result set here. So that's going to give you the so-called second order derivative now, partial derivative. Okay. Now, in terms of writing, you can write it like this. Okay. Very similar to the straight d, except it's a partial d. Or you can write it like this: 2x axis on a subscript. Or you can write it like this. Okay, either way is fine. Is that good? Okay. Now, you could also be taking partial derivative with respect to y now. Okay, so once you finish this, then you take another partial derivative, but this time it's back to the y. So in this case, you can write it now, okay, differently. So this is partial y, partial x. Or it can be fxy. Okay, or this. So either is fine. Is that good? Yeah. Now I want you to basically, what about if I do this direction here, this way here, right? So you could be doing this way here. Okay. They look very similar, but they're not quite the same. So at least in terms of the way you write it, it's different. Okay. So at least the way you write it is a little bit different here. Okay. Yeah. Now, however, as we're going to learn, I'm going to point it out. Actually, maybe I can point it out here. Typically, okay. So this fxy is going to be equal to the fyx, okay, if the function f, okay, is a nice function. Okay. So I use a very lay words here. Nice function basically means it doesn't have like a sharp bump in the middle of nowhere. Or in singularity, that type of things. Okay, so that's basically what we call nice function. And well, we'll give all this not so nice function to the math department. So we're going to deal with this all nice function in this class here. Okay, so bear in mind. So most of the time you're going to deal with is fxy equal to fyx. Okay. Yeah. Okay. Good. Now back to the calculation, the computation of partial derivative. So then how do we calculate the partial derivative? So let's go back to the definition in here. Okay, go back to definition. Okay. What's the definition? The definition is, for example, if I need to calculate partial f with respect to x, then we let x have a small change, right? At the same time, what happened to the yz? They are, is there any change? No, right? So they're being kept as if they are constants. So now the things actually become so clear. When you take partial derivative with respect to x, in your mind, you're going to have to treat the z and the y to be constant. But you have to tell your mind, okay? But then your mind always tells you otherwise. Okay? So that's the trick part. Because your mind always thinks the y and z, they are actually variable. But in this case, you're going to treat them as they are constants, right? So let's take an example here. Okay, let's take a look at this one here. It's a little bit involving the chain rules, but that's okay. Yeah. Okay, so this is a function of 3 variables. This is actually a function of 2 variables here, so only x and y here. If I need to calculate partial f over partial y, okay, yeah. So there's something now you had to get comfortable with. So you're taking partial derivatives with respect to y. So what do we do with x? You treat x as if it is constant, right? So if your mind doesn't work that way, you can temporarily change the x to an actual constant, right? To a 2 or 3, but then remember to change it back though, right? Yeah. Otherwise, if this is being treated as a constant, then instead of partial, it's like df over dy now, like the regular way you're doing it, right? But you can't write it as a df over dy. You still have to write it as a partial f or partial y, right? Okay. So there's a y here, there's a sign here, so there are 2 part of function. So you actually need to use the product rule. Okay? You can think of this as a u of xy and v of xy, like this, right? So u of xy is y, v of xy is sine xy. Okay? So basically, product rule, derivative. So a derivative of a part. First part is a u at here. It's like this. Okay, it's like partial u over partial y times v plus u times partial v over partial y. Okay? Yeah. I mean, except that the u is actually just a function of y. So partial y over partial y is. So this portion in here is what? Just partial y over partial y. It's actually dy over dy, right? Times v times sine xy. And then y times partial over partial y, okay, and sine xy. So if I write it in detail, that would be this. And when you have more experience, you don't have to write all the detailed steps. You can actually skip a few steps here, right? So this is basically sine xy for the first term. And second term here is y times the partial derivative of this term with respect to y. So if you consider x as a constant, what do we get? We get x times cosine xy. Good? Yeah. So the key is to make sure that you keep telling yourself which partial derivative you're taking. What do you do with the other variables? Right? Yeah. And then the rest of the work is basically the same as single variable derivative. Is that okay? Yeah. Okay, so I think that's fine with this question right here. Okay. Yeah. So before we move on in here, so let me maybe touch upon a very simple one in here. So let's think about a little bit basically the concrete meaning for partial f over partial x at a certain point. Okay? Yeah. Now in this case, I'm going to use a function of 2 variables to illustrate this idea. Okay? Yeah. So let's say I have a function of 2 variables. So now I'm going to go into 3D space. When you have a function 2 variables, you can always basically construct yourself, okay, with kind of surface, right? So that's your z equal to f of x, y. Good? All right. So now, if I'm going to use the definition first, what is the partial f over partial x at a certain point? Okay, at a certain point. So basically, let's say if I start from this location here. So this is your x naught, y naught location. Okay? Yeah. Then according to the definition of partial derivative, right, it basically means you start at x naught, y naught location, then you increase the x naught by a small quantity delta x. At the same time, you're not going to change the y value, right? So that's the definition of partial derivative. Okay, that's the definition of partial derivative. So if I look at the operation-wise at here, basically what it means is, okay, starting here, this is your x-axis. You move to this side here a little bit until you're at x naught plus delta x, and then at the same time you keep the y naught the same, right? Okay. So it's like the way you go is you're coming from here, and then you go all the way to this direction, to the x-axis direction. Does that make sense? Okay. So now, if you imagine, right, when you go from here to here, what happened to the value on the f of x, y? So it comes from here basically to here, isn't it, right? Okay. Yeah. Now, for this equation in here, so then what it happens is, right, your y is not changing. If I'm gonna, like for example, if I'm gonna look into this direction here, right? Look at this direction here. Okay. What do you see? You basically you see it's for you when you look at from this direction in front of you. All you see is a plane, isn't it? Right? All you see is a plane here. So you basically see it's a curve, and then you have a straight line in here, right? It's like this. Okay. It's the same way as if you're doing a single variable function. All you see is essentially you're looking at is a slope. That makes sense, right? So the rate of a change of the function f with respect to the x, it's a slope at here. So if you draw a slope crossing that x naught, y naught, and the z naught point, that line has a slope, and this slope is indicated by this partial derivative. Does that make sense? Yeah. So partial derivative at a certain point with respect to x, basically it's a slope. It's a slope representing the curve, okay, when you are going from here to here and traced out from this surface z equal to f of y. Okay? Yeah. And similarly, partial f of partial y will be a curve on the other side here, right? Yeah. So that's what the partial derivative means. So see, what I'm saying at here is it's a slope as you're going along the direction of x-axis, right? Yeah. Remember I said direction now matters. Okay. So in the near future of actually 2 weeks from now, if I go this direction, then I will get a different slope, right? Yeah. That's what I call the directional derivative in the future. Okay. That's not the partial derivative, partial f over partial x anymore. Okay. Yeah. But in essence, for partial derivative, when you do the computation, okay, all you need to do is just treat the other variables as constant, and you do as if you're doing a single variable derivative. That's it. Is that okay? Yeah. That's all about partial derivative. Simply put it. Okay. Yeah. So I have one more topic to finish next lecture. Okay, and which is total differential, and that will be it. Okay. Any questions? Okay.